Now I'm going to introduce the concepts and general features behind an analytical tool called infrared or IR spectroscopy. So IR spec is a chemical analytical method that uses different frequencies of infrared light. Now recall that infrared light is light that's at a wavelength below visible light, and it's going to use that frequency of light to make chemical bonds stretch and bend, okay? In general, we call these changes in the bonds vibrations, okay? So it causes, the frequencies will cause the bonds to vibrate in different ways. Now there's actually a bunch of different types of vibrations that are possible. Stretching, twisting, wagging, scissoring, rocking, that's another one. But for the purposes of this course, we're really going to treat them all the same, and we're just going to refer to all of them as vibrations, okay? Now, the whole idea behind IR spec is that we can use different frequencies of light to make different types of bonds vibrate, okay? Because different bonds will vibrate or resonate at different types of frequencies, okay? And if we plot out the movements of the bonds with the wavelengths of the light that we're using, we can actually get a pretty good idea of what type of bonds are in the solution that we are testing, okay? Now, there is one kind of exception to this analytical method, or maybe a limitation would be a better way to say it, which is that if a molecule is perfectly symmetrical, as an example, N2. So N2 is a gas. Recall that it's a nitrogen, triple bond nitrogen, lone pair, lone pair. There's only one bond there, and this molecule is perfectly symmetrical, so this would not result in my IR spectrum, okay? Now, this isn't something that we really have to worry about in real life, because everything we're going to be analyzing in this course is going to be large asymmetrical molecules, often with multiple functional groups. So we don't really have to worry about this, but it is something to know as a conceptual question, okay? So now what I'd like to do is introduce kind of the general features of the IR spectrum and kind of explain what we're looking at here. Because when we put the molecule inside the IR machine, guess what we're going to get? We're going to get something crazy looking like this. A bunch of peaks, a bunch of troughs. It kind of looks like we're walking into a cave, okay? And we've got all these stalactites that are about to fall on us, all right? Well, these are not stalactites. What we actually call them is absorptions, okay? So I'm just going to write that word here, absorptions, okay? And absorptions are one of the things that we plot in an IR spectrum, because it basically tells us how much of the light is getting absorbed. So let's just talk about the x and the y-axis here, okay? Let's actually start off with the y-axis. The y-axis has to do with transmittance, okay? Now I know you can't really see that word. I'm sorry, it's so small. Maybe you can see it on the paper that you printed. But it just basically says that either 100% of the light is getting transmitted, or it's getting through the sample. Okay, that means that it didn't get absorbed. Or all the way down to 0% got through. If 0% got through, that means all of it got absorbed, right? So this thing right here, this big little like stalactite looking thing would be what we call an absorption. That's an area where that specific wavelength of light did not get through the sample. It actually got almost fully absorbed. Notice that it's all the way almost down to like 5%, okay? So that means 95% of this light, of this frequency, did not make it through the entire sample. Cool so far? Now let's talk about the x-axis. The x-axis has to do with those different frequencies of light, and it's measured in something we call wave number. So I'm just going to write this out again. Wave number. Now, you might think that wave number is the same thing as wavelength, but it's actually not. It's a weird way to measure frequency, okay? So it's measured in centimeters, the reciprocal of centimeters, okay? But really, what this is a measure of is more like frequency. So all you need to know is that as your wave number increases, your frequency also increases of the light, okay? And we've got, it starts off at 0 and it ends up around 4,000, okay? So those are the different frequencies that we're measuring, okay? So now you see you get this pretty graph, you kind of understand the axes a little better. Now how does this actually relate to chemistry, right? Well, basically different types of bonds, as you can see I've already written out some basic functional groups here, some basic bonds. These are going to be the ones that can result in different places on the spectrum, okay? So the first and most important distinction we have to make about the spectrum is that it has two big regions, okay? So we're going to just separate it as the region below 1500 and the region above 1500, okay? The region below 1500 is what we call the fingerprint region, okay? Now, why do we call it that, okay? Because this fingerprint region is going to have so much variation in it and so many different peaks and troughs coming out of it that almost the only information that we can get out of it is kind of like a fingerprint, okay? So you could imagine that if you took my fingerprint, okay, what kind of information does that fingerprint give you? Does it tell you that I am a male? Does it tell you that I am, my ethnicity? Does it tell you, that I like a certain food? No, it really only tells you that I'm Johnny, right? It just identifies me as a person. And that's kind of the information that we get from the fingerprint region. All it really does is it helps to differentiate one molecule from another, but it doesn't tell us much about what the molecule actually is, okay? It doesn't tell us if the molecule is an ether or if the molecule, well, it can sometimes, but it's very difficult to read and very kind of unreliable. So for the purposes of this course, guess what we're going to do? We're going to ignore the fingerprint region, okay? We're never going to discuss wave numbers below 1500. Now, I just want to make a note to say that this is the part where professors can kind of vary, and you may be just lucky enough to have one of those professors that actually cares a little bit about the fingerprint region. So I'm going to leave that up to you as homework to ask your professor, Professor, is there anything I need to memorize about the fingerprint region? But for the purposes of clutch prep, we're going to focus on everything above 1500 because that's the part of the spectrum that's much more commonly tested, okay? So now that I've said that, what's the part that matters? The functional group region. Functional group region, okay? Now the functional group region is the region that actually we can get information about the types of bonds, the types of functional groups. It actually tells us what type of molecule we're looking at, okay? Now you notice that I also have these kind of lines in between in different areas on the spectrum. These lines represent different themes or different types of bonds that I can see in the spectrum. So the fingerprint region is going to be the region where we see single bonds, okay? So I'm just going to write this here, single bonds. And this is where bonds like C single bond C, C single bond N, C single bond O, C single bond X, recall that's a halogen, right? So single bonds are going to result in that region of the spectrum, okay? Now, that does make it challenging because you can think that a molecule is going to have lots and lots of these single bonds. So this spectrum, this part of the spectrum is going to be a mess. It's going to be a collection of a bunch of different things coming from all those single bonds, okay? So we're really going to pretty much ignore all of those bonds, and we're going to focus on the ones that are in functional group. Well, what kind of bonds do we get in the functional group region? Well, we get, for the range between 1500 and 2000, we get the double bond region. Okay? Now, the idea behind the double bond region being a higher wave number than the single bond region is that these molecules are going to vibrate at higher frequency when the bonds are stronger, okay? So if you can imagine that this bond is kind of like a spring, and when you have a really, really tight spring and you flip it really quick, or you just put your finger on it, it's going to vibrate really, really fast, okay? And when you have a loose spring that's not really that strong, it's going to vibrate a little bit more slowly, okay? Well, double bonds are stronger than single bonds. So I would imagine that it's going to vibrate at a faster frequency than a single bond would. And that's why it's going to result at a higher wave number. So the types of bonds that we see in the double bond region are like C double bond C, C double bond O, C double bond N, even like when you have two double bonds in a row, that's called a cumulene. You could even see something like that, okay? So pretty much anything in the double bond region is going to be between 1500 and 2000. That's because it's going to vibrate a little bit faster than the single bonds would have. Well, now that we talked about double bonds, what do you guys think comes next? What's the next stronger type of bond? You got it. So the next region between 2000 and about 2500, this line is actually a little bit further than I would have liked. The spectrum, it's not drawn to scale. But from about 2000 to 2500, we have the triple bond region. Okay? And the triple bond region is going to vibrate even a little bit faster because it's stronger. And this is where we're going to see things like C triple bond C and C triple bond N. Those are the two most common types of bonds that result there. Okay? So now we've done single, which we're going to ignore, double and triple, that are both in my functional group region. What do you think comes next? What's going to be the next type of bond that's going to vibrate even faster than triple bonds? I really hope you didn't say quadruple bonds because those are very rare and they really wouldn't work with a lot of the molecules we're using. So it could be a mystery. I'll just tell you. It's actually going to be single bonds again. Wait for it. It's single bonds to hydrogen, okay? The reason is that hydrogen is the smallest, lightest element. So even though the single bond is not that strong by itself, it also has a very tiny thing on the end. So if you can imagine that this spring is very, very light because it has this very little atom on it, it's still going to vibrate really fast, even though it's not a very tight spring. Get it? So the hydrogen makes it actually vibrate faster than even a triple bond. So what kind of bonds do we see in the single bond to H region? Well, that's where we're going to have our CH, our OH, our NH. I'm just going to dip into it a little bit. Pretty much those are the ones that we're going to deal with, okay? We're going to see a lot of those. And that kind of explains the general regions of the spectrum, okay? Now, it does get more complicated because we're actually going to have to memorize the absorptions of different types of bonds. But for right now, even if you forgot the exact absorption, and even if all you knew was these regions, it already gives you kind of a reference point to know where would this thing tend to result. Okay? So now what I want to do is just go over quickly, because we're going to do this in more in more depth. I want to quickly go over just some major absorptions and kind of show you where they would result here. So as you can see, my double bond CC and my double bond CO both result around the same place, okay? Now what we're going to notice is that later on when I talk about this, I'm going to go into more detail about C double bond O especially. It's not always at 1700, but it's in the range, okay? So you could see this definitely puts it well within the double bond region, okay? And what we're going to notice is that I have these words over here. What do these words represent? Well, I've got words like strong, medium, and then comma, sharp. What is that talking about? Well, it turns out that, I know this is a lot to explain, but scientists can never just use common words like normal stuff. They have to make up their own, right? So the first word, the very strong or medium, okay, so I'm just going to say that the first descriptive word, okay, is actually talking about the size of the peak, okay, or the size of the absorption. So basically, the first word has to do with what we could call length, okay? So very strong would mean that it's a very long absorption, and medium or small would mean that it's a very short absorption, okay? So that's the first word. Then we have the second word. So I'm going to put comma, second word. What does the second word represent, okay? Well, that's going to be words like sharp or broad. As you can see, I've got here broad. So that word represents the width, okay? With sharp meaning that it's very narrow, okay? Think of it almost like a sharp stalactite. If it falls on you, it's going to cut right through you. And then broad meaning that it's very wide, kind of like if it fell on you, it would just crush your entire body. It wouldn't split you in half. This is getting gruesome, so I'll stop, okay? But you can see that basically when we describe them, we're usually saying length and then width, okay? And as you can see, these ranges here, I'm actually going to take myself out of the camera really quick. Ooh, I just messed that one up, sorry. Okay, I'm not taking myself out of the camera, but I'm just going to step out of the way to show you that the absorptions are actually very similar for these guys, but their shapes are different, okay? So that's what we're going to focus on in the double bond region, that their shapes are very different. Now when we move on to the triple bond region, we see that triple bonds tend to result around the same place, but safely between 2,000 and 2,500. And then we see that all of our bonds to H result in differing places depending on where they are, but they're all, in the 3,000 range or more, okay? So what I'm going to do is, during the course of this lesson, I'm actually going to go over much more specifically what all of these different peaks look like. But for right now, I'm just trying to give you kind of a general framework so that later on when we discuss the exact shapes, you guys will be able to recall how it looks on the actual spectrum. Okay? So with that said, let's go ahead and move on to the next part.